Good evening, everyone, and welcome to IIT Madras' Institute Colloquium. Today's lecture is titled From Molecular Acorns to Institutional Oaks and will be delivered by Professor T. Pradeep. First of all, I'd like to welcome Professor T. Pradeep for agreeing to give us this lecture. I'd like to welcome the Dean of Academic Research, Dr. A.K. Mishra, for gracing this event with his presence. I'd like to welcome the Dean of IR, Professor Nagarajan, and the Dean of Students, Professor Shivakumar, and all faculty, staff, and students for being a part of this event. I invite Professor T. Pradeep and Professor A.K. Mishra to take their seat on the stage. I request the Dean of Academic Research, Professor A.K. Mishra, to present a fruit basket to Professor T. Pradeep as a token of our appreciation. I call the Research Affairs Secretary, Mr. Ashok Kumar, to present a fruit basket to the Dean of Academic Research, Professor A.K. Mishra. I invite the Research Affairs Secretary to speak a few words about the chief guest.
Thank you, Ram. So I'm extremely happy to introduce our chief guest, Professor T. Pradeep from the Department of Chemistry. Professor Pradeep is an institute professor at our institute, and he is the highest title professor that any professor can earn. He is also the Deepak Parekh Institute Chair Professor and Professor from the Department of Chemistry. He earned his PhD from the Indian Institute of Science in 1991, and he has postdoctoral training at the Lawrence Berkeley Laboratory in University of California. He held as visiting professor at many leading universities and institutes in Asia and Europe. Professor Pradeep's research interests are in molecular and nanoscale material, and he developed instrumentation for the same. He had authored more than 394 scientific papers, and he is an inventor of over 75 patents. Professor Pradeep is also one of the highest cited author in IIT Madras, with an H index of more than 64 in Google Scholars and 54 in Scopus. He is involved in the development of affordable technology for drinking water purification, and some of his technologies have been commercialized also. His pesticide removal technology has been incorporated in 1.5 million filters, and the technology is estimated to have reached 7.5 million people in near future. Along with his associates, he has incubated 2 companies. One of them has a production unit too. He has written several books, and he is also author of one of the books called Nano, the Essential by the Tata McGraw publication, and also one on nanofluids. He is a recipient of several awards. I am extremely happy to have you on the stage, sir.
Thank you, Ashok. I now call the Dean of Academic Research, Professor A.K. Mishra, to say a few words about the Institute Colloquium.
Professor Pradeep, my esteemed colleagues, the guests for this occasion from outside, and student friends. This is a part of lecture series that are designed for our institute professors to be telling about their achievements in life and to be telling the audience, essentially, how they have been different from others to become an institute professor. Actually, we didn't have a really good faculty recognition system earlier. So about 5 years back, we had this system called IRDA, the research award system that we have. And in this, the highest level of IRDA award is called the Institute Professor Award. It's also called a Lifetime Achievement Award. So needless to say that Professor Pradeep, who joined 3 years later than me, he still has a long time to go. And already 2-3 years back, we honored him with this Lifetime Achievement Award. Speaks volumes about his achievement so far, and there is a long way to go. It's an honor to be listening to him now, today, and I'm sure there will be many more such occasions that we will be again listening to him when the awards grow in size and recognition grows. Right now, as you can see, from what you hear from our Research Affairs Secretary, he combines in him a lot of excellences, like in academic life that you can think of. Excellence in research, excellence in teaching. Some of his books that he has written are remarkably good. Excellence in entrepreneurship, the kind of companies that he has incubated and nurtured, and the way they are growing. Amrit is already the water purification system is already a talk of town. Excellence in social responsibilities, and you name it, he has done it, and a lot of things to come still. So it's my pleasure to invite him. I don't want to take too much time between you and him for talking about his journey in his life till so far. Professor Pradeep.
Thank you, Ashok. While standing here before you, obviously many things rush to my mind. Many which are stimulating, invigorating, a few disturbing. All of these collectively rush into and stimulate my neurons. But one thing stands out. What stands out is that institution has undergone a rapid change. And my institution has begun to appreciate and celebrate the work of students, staff, and faculty. And I stand before you because of this long effort of that celebration. So first and foremost, I'm thankful to this highly happening place today. But then I salute a lot of people because of their thankless efforts. We are in a position to celebrate this. So while I stand before you, many of these people rush to my mind. As I stand here, I did have an opportunity, for several months to think about what to speak. I could take a topic of my research, a paper, and then tell you that in some detail. I could tell you about a patent and its translation to societal benefits. I could tell you the work of a PhD student and the celebration of that individual, transforming that individual to a great independent scientist. I could tell you about building a laboratory. But then I decided that I would probably combine all of those and tell you something about this, which I say is building institutions, transforming things right from scratch. And this is obviously my journey, and it could be your journey. And in this process, the objective of this talk, therefore, would be to see that some of you can walk probably much faster than me and do much more. So it has been 24 years for me. Some of you may not have been born at that time. So many things can be done probably much faster. And in that process, many things have been incubated. And in fact, this little company has just got its name today. So this is what has happened in the past several years. I should tell you, this is not really working. So that journey has been pretty long and quite tiresome for me. It could be much faster and much easier, much enjoyable for me. And all of us have been sort of trying to create a system wherein it will indeed be easy for many of you. And that's what Ashok talked about. With that, let me tell you in the next 60 minutes or so, and you can expect this lecture to go exactly to 60 minutes with about 5 minutes of acknowledgements or so. So this would be a celebration of chemists. Chemists look at world very differently. They look at molecules, but then they translate these molecules to something physical realities. So chemists, there is no surprise that a chemist would see something like this as an adsorbed molecule. A chemist would look at something everyday object, such as water, to something which is molecular. And chemists would obviously look at this molecular thing as everything, this large drop, to be composed of chemical bonds, hydrogen bonds. In fact, these molecular bonds have defined the entire properties of this very large system. So if you start looking at a very large body, such as our planet or things beyond, you would see these chemical bonds coming into play in many, many ways. I have no time to tell you all those great celebration of bonds, that celebration that we have been enjoying in the past 100 years or so. But I will have something to tell you about that molecule, that is this molecule of water that I talked to you about. This molecule of water that I just mentioned is finite. This is that many molecules of water exist on our planet. Because of very interesting chemistry, we don't make new water molecules. Of course, we transform one molecule to the other. In that process, water is born, such as combustion. But this water was there originally. So in fact, we don't really produce new water molecules. But we keep modifying this water in different ways. We keep contaminating this water in different ways. Our entire process of industry has been just this. So in fact, just like thermodynamics, you might say that pollution or contamination has been increasing with time. This water has been a subject of a lot of attention. A lot of people have researched on this. In fact, this is the most celebrated subject, but not very well understood. About 10,000 papers are published every year on water. And this water is also important in many, many different ways. So I took one slide from UN to say that of the 17 goals, sustainable development goals that we are supposed to achieve in 2030, look at all of these. All of these, by and large, is related to water. No poverty, zero hunger, good health. Education also has something to do with water. Gender equality, clean water and sanitation. You look at all of these, most of these, there is a central theme of water in different ways. If you look at opportunities in the country and elsewhere, this water presents numerous opportunities as well. these many people don't have clean drinking water. You can get all these statistics from books or internet. More than 2 billion people worldwide rely on wells for their water. By 2025, an estimated 1.8 billion people live in areas plagued by water scarcity. All that, many more. But important thing is that here in India, 67% of Indian agriculture is based on groundwater. And you see the global middle class will surge from this, and most of this surge is happening in India, and we have no fresh water. So you can go on and look at this. You might have seen just today in the newspaper, the global hunger index has come. And this hunger index, India is 100. 100 in that list. And in fact, India keeps on going down. Even, India is the second larger producer of food grains, but hunger is most severe in our country. So one can go on connecting all of these to water. You see that these many millions suffer due to arsenic. I put this dash because this statistic keeps changing. These millions suffer due to fluoride, and these are happening right here. And many places with uranium have been found. Unknown kidney disease and many others are just around, and we are finding very many new things. And if you look at all of these, 2030, we will have to certainly take a bullet train to have, to eradicate hunger. So if you look at a WHO statement, long-term exposure to arsenic from drinking water and food can cause cancer and skin lesions. It has also been associated with developmental effects, cardiovascular disease, all that. So you would say that all of these would certainly make a significant fraction of the population incompetent. They cannot compete with others. You are obviously having no liberty, equality, and fraternity, the celebrated goals of French Revolution. So when you start looking at problems of this kind, you realize that science has to do something very important. Arsenic in the country is 102 years old. Fluoride in this country is close to about 80 years old. We have still not been able to solve this problem. We have still not been able to find affordable solutions. So it is in this context that we started looking at translation. So let me give you an example of this translation, and where one can do chemistry. So this is a little device which produces water from a depth of about 80 or 100 feet. And bottom of this little cement terrace that you see is this iron stain. This iron stain tells you that in this particular region, there is arsenic also in water. Arsenic you can't see, iron stain is what you see. Along with iron, something that comes in this region, unfortunately in this particular pump, what is there is arsenic. We have put a little product here. So this boy, let us say a 10-year-old kid, pumps water from a depth of whatever. One stroke in 3 seconds produces 300 liters of water. So this 300 liters of water, in just about 2 seconds, you could clean that with this device and get you arsenic-free water. Now, with no additional pressure drop, with no delay, you could get 1,000 liters of water every day. And you can do this for 1.5 years with a device of this kind. So fantastic. So is it possible that you could put a material, something, right into this? This itself has been tremendous, a fantastic task of several years, but is it possible? And you ask this question, is it possible to produce new materials? So if you look at that story, you have clean water on the surface of Earth just because chemistry permits it. So if you look at the surface of Earth, which is composed of aluminum oxide or silicon dioxide and all of these, they have solubility products of the order of 10 to the power minus 35. That is why you have no aluminum or none of these contaminants in water. But our chemistry that we have found over the years, we have industrialized over the years, produce materials which have large, very large solubility products. So that is why water gets contaminated. Well, arsenic is not this particular story. So why is this nanotechnology we are talking about? Nano obviously is very big and gets into every subject area. However, this smallness of nanoscale materials is what one is interested in, just like quantum. So there are many such materials. All of you might have seen some materials of this kind. There's a variety of such materials. But good thing about this is that all of these you can produce in just 1 hour, right from one simple raw material. So good thing about nanomaterials chemistry is that by doing science in a slightly different fashion, starting from one material, you could produce all of these in different ways, in just about 1 hour. What does that mean? All of these materials have different properties. Just like, water is something, just change it slightly, it becomes hydrogen sulfide. Change it slightly, it becomes an ether. All of these are different molecules with different properties, with a different smell, different melting point, different all that, right? All different colors and all that. Just like that, you can create different properties from one element in just 1 hour. Think about this. Some years ago, as organic chemists, you would add carbon, nitrogen, hydrogen, oxygen, and all of these in different proportions and different ways over several tens of steps to create new materials with different properties. But here, with one element, you could create all that very fast. So this is the power of nanomaterial science that we have found in the recent past. So to give you an example, you have some material which looks like quartz. But you expand a corner of this little, this material, you get something like this, which is actually composed of small particles. So if you expand this particle further, you start seeing atoms. So you can create structures of this kind just from one element. Why are you interested in this thing? You're obviously interested in this because there are so many different properties that you can incorporate into one material and get you new things. I have no time to tell you all that, but to tell you that if I were to create a bottle of materials composed of these small particles, I would essentially be in a position to achieve more properties for less amount of material. So this is essentially the large benefit of something called surface area. But then that's not the only thing. Look at this, limits of contaminants. Today, if you take a glass of water, contains, let me show you this. A glass of water contains 200 ml of water, or about 200 gram of water, and which is about 10 moles of water. 10 moles of water is about 6 into 10 to the power 24 molecules, or something like 10 to the power 25 molecules. In that 10 to the power 25 molecules, for many of the toxins that we have produced, the amount tolerated is 10 to the power 12 molecules. So that means 1 out of 10 to the power 13, 10 to the power 12 out of 10 to the power 25. So 1 out of 10 to the power 13 is the contaminant that you can tolerate, or you would like to remove contaminants to that efficiency. Which means that think of a water purifier. And this water purifier is producing 10 to the power 25 molecules in 1 second. And you want to stand there in 2 minutes or 2 seconds, you would like to clean up all those molecules with efficiency such that only 10 to the power 12 molecules remain in 10 to the power 25. Which means that you pass a very large number of molecules through a little opening and separate out all those contaminants which are needed so efficiently. Let us take an analogy. Indian population is 1 billion, something like 10 to the power 9. And 10 to the power 13 is 10,000 Indian population. Pass 10,000 Indian population through Chennai airport entry and then filter out a terrorist from that in 1 second. This is just impossible. And that is why molecular nanotechnology is important, and many people think that that is the way, that's the direction forward in filtration. I do not have time to tell you that a great endeavor globally, but this is how molecular technologies are progressing. Is it really needed? The need for this comes because many of the contaminants in water, as we went on understanding the contaminants' implication to health, the concentration of tolerated contaminants start declining. So they reach this kind of limits. So take arsenic. This was the contamination permitted in 1959. This is the contamination in 1976. This is what is in 2001, and many people think globally that the contamination arsenic should be 2 ppb, and at least 2 nations have brought it down to below detection limits. And we know from chemistry, from biochemistry, that even at 170 picograms, arsenic causes genetic deformation. So you would like to get to this kind of numbers. Is it possible? Here is an example from our own science to tell you that a material of this kind transforms to this just with 9 ions of mercury. Meaning that chemistry can be so sensitive to remove, to detect contaminants at that level. Globally, there is a lot of such effort. Very many such materials are getting formed or made, cavities, channels, imprints, and many, many others. So if you look at nanotech, globally, it is new adsorbents, new sensors, new catalysts, a novel phenomena with aquaporins and things like that, new devices, all of this is coming. And we have been instrumental, at least in some of those areas, to sort of create new science. To give you an example of what these new materials can do. So you look at arsenic, as I just told you, for 4,000 liters of clean water you want to produce, let us say 10 liters of water per day, about 4,000 liters per year, if this is what you want to produce for a family, this water contains about 200 micrograms per liter in West Bengal. That means you want to remove these many milligrams of arsenic. So today's materials have a 2 milligram per gram capacity, and therefore you require about 400 grams of this material. Many nanomaterials, this can be brought down to just about 16 to 20 grams of material, which means that in that filter that I told you, because of that, you could produce 10,000 liters or 1 lakh liters in a few days, even with a smaller device of this kind. But if you really utilize the limits of these materials, you might probably be in a position to pack a little cartridge into that water pump itself. So the research comes in because you could ask these questions: is there a process fast? Is this require power? Is that cheap? Is that environment friendly? Is that sustainable? Is that design is adaptable? All of these. Obviously, new materials can be produced, new methods can be produced, new analysis is obviously required, and all of these have to be done at the atomic level. So my science has been to create inquisitive science, a lot of these in different areas, technology transfer in this area, and then look at what is the future, and I'll tell you glimpses of all of these in the course of time. So if you look at, can somebody stop whatever is going on here? Noise that's coming. So if you look at materials, the materials today are so precisely defined, so I could make these in the lab with synthetic chemistry. This would be called a nanomaterial, but this nanomaterial is not an ordinary material. This is atomically precise. So I know precisely how the atoms are, I know the structures. So these materials are called clusters. And they are new, very new, with very new properties. So this is a luminescent particle of a metal, which is very familiar to you. This is silver, but it is luminescent. And this was unheard of till about 2009 or so. And we can today produce this in quantities, such large quantities that we can have a kilogram of this. But we can have a gram. This is what a few grams that is made in the lab. A lot of such molecules come. But the point is that you can define this in great detail. So this is a molecule. So for me, this is a molecule. And what it means is that molecular science can be done on this. So here is a mass spectrum of this molecule which we make in the laboratory. So you see, a nanoparticle is now having a mass with an accuracy of 0.5718, meaning you can do ultra high resolution mass spectrometry with just this number. I know the precise formula. So this we organic chemists call as high resolution mass spectrometry. Remember, now nanoparticles, you can do high resolution mass spec. So if I take this little peak and expand this, I see all of these. This is incidentally a molecule of gold. And now, good thing is that this molecule can be crystallized. And this molecule, very many new things are possible. Some of them are, of course, useful for water. Let me show you one example. Some years ago, I was asking this question, these are all molecules. So is it possible that they will do reactions just like molecules? Remember, some years ago, for a lot of time, like people like Rangarao sitting here, we've been looking at nanoparticles and reactions on them. Dilip is not here, but he has been looking at things like that. Manoharan looks at. So reactions using nanoparticles. But is it possible to think about nanoparticles as reagents and do precise reactions? If you want to do this, you need to have precise nanoparticles. And when you say reaction for a chemist, which means chemical bond transformation. So precisely you should be in a position to say which bond is undergoing transformation. So I'll show you an example. So here is one molecule of this, which I, for convenience, I call gold 25, although there are so many other things attached to it. This I call silver 25. I just mix these two. And you see, gold 25 will give you a mass peak, silver 25 will give you a mass peak, and this is what I'm supposed to see. I'm supposed to see a gold 25 peak and a silver 25 peak. Silver is less in mass, so you are supposed to see two peaks. But just after mixing, very many new peaks come just because one gold atom goes into the silver and one silver goes into the gold. And how does it happen? One gold goes from one thing to the other and no change happens in its overall system. This is because these two particles will come together and form a transition state. And they come together and form a species which is just an adduct. And from that, new peaks come up. And I have a lot of details about this, but we have a structure for it. What does that mean? You can do a transformation such that some gold atoms will come into a silver. So some silver 25, I can add a little bit of gold atoms from this gold 25, and this gets richer in gold, meaning the mass increases. It gets further richer if I were to add some more gold, 25, further, and I can ultimately get gold 25 starting from this. Meaning that I can completely transform a structure, although this is not alchemy, you can transform a structure to another an equivalent structure of another element. Gold 25 and silver 25 are identical structures. So as a chemist then, you can ask this question, where is this silver going? How does it do that? Can I understand the process? And you can then ask questions. Are there mechanisms for this chemistry? Can you create isomers? can you please nanoparticle chirality? You can ask a number of questions. Just as organic chemists draw structures, you can draw structures for nanoparticles. And in order to do this, we have to introduce a nomenclature. So we introduce a nomenclature, and a nanoparticle can be drawn by a structure, and you can write an IUPAC nomenclature. You can draw on a blackboard, you can draw a structure. I will not bother you with a lot of details, but to tell you that a nanoparticle system can be drawn. What does this mean? You could probably look at chemistry or material science or physics of large nanoscale systems analogous to molecules. Oh, I said nanoparticles interact. Ananya here in the audience says that this nanoparticle interaction you can actually see in mass spectrometry, and you can get a spectrum, not just a nanoparticle, but its dimer. It's a dimer, or it's a trimer, meaning that you can create such structures. Somebody else in the audience says that two such clusters can result in new alloys. And a lot of very many new things can happen. I just touched upon something very interesting to tell you that in a bottle, a nanoparticle is undergoing a lot of interesting processes, which I call nanoparticle dynamics. And this nanoparticle dynamics is so profoundly exciting that it is probably possible that their entire behavior is like molecular. So here is an fantastic molecule, H2O, and if I react with D2O, all of you would know that it becomes HDO in no time. Does it happen in nanoparticles? Very recently, we have chemistry to say that this indeed happens in nanoparticle systems. I will not get into these details. So what is that, this kind of science with molecular details that you can probe? How does it tell you, how can this be used for water? So some time ago, we said these nanoparticles, their science can be used in a very well-defined fashion to destroy bacteria, to destroy viruses, to convert molecules, contaminants. And this, we introduced a technology based on this, which would contaminated water can be passed through biopolymers and get them purified. So what is this? In water, there are so many contaminants. 21 contaminants in water are halogenated organic. These are the regulated contaminants. All of these regulated contaminants, if you add together, it will be 92 contaminants. These are new contaminants which are emerging. But if you look at these 21 of these, 15 of these metals, 13 of these organochlorine pesticides, you can control all of these by very interesting chemistry. And some years ago, about 15 years ago, Sri Kumaran sitting in this audience showed that it is possible to break pesticides using nanoparticles. So it became a product, and it became, it was sold in several millions. So this became a very interesting theme. We continued on. So the last paper that I told you said that affordable materials can be produced by bio-inspired chemistry. So what is this? We have styrofoam, and we convert this to water purification materials. In the process of producing these polymers, you use water. In their useful life, they of course produce water. But when they are put back in the soil, they destroy or they use water. So if you ask this question, is this material water positive? Totally, are you getting clean water from this material? Many of these are really water negative. So is it possible to create water positive materials was the question that we asked in this paper. And is it possible that such materials can be synthesized in water without using electricity at room temperature? This is something, a very interesting task. You look at silica. Silica that is there was born at high temperatures. Is it possible to create that stable silica at room temperature? Is it possible to create alumina at room temperature and water stable? So we created such materials, therefore they are green materials. So this was the substance of this paper. So what we did was that we have biopolymers, and these biopolymers, which are soluble in water, were converted to stable materials which have Young's modulus equivalent to silica or sand outside. And these have structures like these, which are about 50 nanometers thin, sheets about 50 nanometers long, and you can pack these sheets like that with biopolymers, interlocking them, creating cages. And in these cages, you can put nanoparticles. And such nanoparticles, very interestingly, you can put water through it. Water will go in, nanoparticles will leach out something, these ions can come out into water, and they can be used for disinfection. And these nanoparticle surfaces will not be coated with contaminants present in water, because those contaminants will not get into these cages. So this is quite interesting. How is it interesting? Look at, let us say, this nanoparticle is silver. And that releases 50 parts per billion of silver over a very long window. You can measure it up to 6,000 liters. If you do this with normal silver particles, you will see that it will produce, of course, silver ions, but just about 20 liters of water or 100 liters of water, it will fall down, and then no more silver will be produced. The reason is that real water contains a number of ions like silicate ions. They go and sit on these surfaces of silver nanoparticle and produce a very tiny layer of calcium silicate, which is just about 50 nanometers thin, and that is enough to destroy this concentration. At this concentration, which is below the permissible limits, you can destroy these living bacteria to dead bacteria. You can kill them. And this works, of course, at high TDS. Even at high TDS as present in our waters, in IIT Madras, we have TDS of 800 oftentimes, or even 1200. And that is the input water, and it containing bacteria, and it can be brought down. And this kind of pH you may have, you can bring this concentration of bacteria down. This may be the humidity that humic acid concentration or total organic carbon present, you can bring even in that concentration, you can bring bacterial concentration down. Oh, so is it that nanoparticles you're using? Is it nanoparticles are getting into bacteria? No, nanoparticles can be deliberately put into bacteria. And you can do single particle spectroscopy to prove that these are indeed nanoparticles. But in our case, you are putting ions into these bacteria. You are destroying bacteria, but no nanoparticles are put in. And this is not just one bacterium. Many bacteria you can do spectroscopy. So you ask this question, does it leach out aluminium? No, it doesn't leach out aluminium, because this contains some alumina structure. Does it release organic carbon? It doesn't release organic carbon. So you can produce, a prototype can be produced. You can put in water containing all of these contaminants, and you can ask this question. Hey, input water, this is the output water. Is input water containing lead or arsenic or something? What is it that you get out? Now in this kind of thing, you are leaching out silver ions into water, and this water is interacting, or thus ions are interacting with bacteria. When this water containing metals or contaminants pass through another filter, this filter removes the contaminants other than bacteria. So we have to create multiple materials. So Anil, sitting in this audience, he made a very interesting nanoscale material. This is, of course, you do spectroscopy at a nanometer level to prove what kind of particles are present. But most interesting aspect here is that you can put this material in a filter like this, pass contaminated water through this. This is iron and arsenic containing water, and you can get that. So this product, you have about 30 grams of this material, but it removes water, containing arsenic, about 1,200 liters. And you can make a domestic purifier. And that domestic purifier runs for 6,000 liters. That was the input water concentration are 200 ppb, and this is what you get as the output water concentration. This is the iron, which is about 4,000 ppb or 4 ppm, and this is what the output water you get. And that is measured for a long time. And you understand how this science happens. This happens on these nanoparticles, specific sites where this ion called arsenate and arsenite sit in a particular fashion. Sudhagar in this audience looks at these, a single particle, and it is how particles are picking up arsenic, the structure of these in great detail. Earlier I told you that single particle spectroscopy. But the single particle spectroscopy can be done today in the laboratory, not just spectroscopy using scattering. Today, from a single particle, you can measure a Raman spectrum. So this is a single particle that you're putting, and this boy, also sitting in this audience, can collect 1,000, 10,000 spectra from a single particle in a few minutes or hours. And he can put all that thing together, and you are actually seeing transformation of molecules on the surface, and you can see on a single particle how molecules undergo transformation in real time. And this is not the only thing. And such science, obviously you do it in many different ways. Swati, sitting in this audience, is using these nanoparticles more efficiently. She says that by putting a little bit of carbonate in water, you could put more silver ions into a virus. So here is without carbonate, this is what you can put in. This stain is because of silver, but with carbonate you can put in for the same silver concentration much larger. In fact, by the science, she says that the silver that is used for antimicrobial disinfection can be brought down by half. So that means about 1,250 tons of silver saved globally. So what does this mean? You can take all of these science to translation. So here is a product. At one point in time, somebody in West Bengal, a district collector, thought that something that we are using can be put in the field. So he put a little product in the field. In fact, we put the product in the field, and he was monitoring it without we knowing about it. And after 2 years of monitoring in this district called Murshidabad, the district in the state called West Bengal, and in this Murshidabad district, 100 such installations were made. And today, these installations have gone from domestic, this kind of industrial units have been there in the field. About 40 cents of land is required to produce this or install this kind of purifiers or purification units. Today, all of these can be brought down to about 7 cents of land because these materials are highly efficient. And we monitored the concentration in the input water, and this is the output water over several days. Today we are not monitoring, but we see that concentrations as high as these can be brought down, and we continue to monitor in some cases. Today, we have gone to different states. So this is now our activity with this company, and we have new installations, more and more of these installations. Obviously, when we start putting something in the field, you ask this question, hey, is this what happens when there is diverse water quality? What about spent media? What about sludge? What about reactivation? What's the cost? How about weather conditions? All of these, we have looked at in great detail. Many people have looked at these as well. And if you are interested in a summary of all of these, is there in the literature. But this is not enough. We have to think about new technologies. So here is our new company, which produces capacitive deionization. So what is that? You have electrodes stacked one after another, and you have positively charged electrodes and negatively charged electrodes alternating each other, and water goes through containing salts, and they get separated, and you get clean water. Today, this can be put in the form of a little box, and you can have commercial products of this kind. This kind of a technology is very much useful because here is our coastal areas. 70% of the people living in these coastal areas are suffering from seawater intrusion. So brackish water is a very serious problem. And it is possible that you can remove all these ions very effectively, and the potential that is used is just DC and just below 1.2 volts. below the electrolysis window, so you can take power from the sun and have desalination. And this product today is there sitting on top of the TUE terrace as a commercial unit. And Vijay Sambat sitting in this audience, I would like him to come and give me a glass of water from this new product, which is just going to be released in about 3 months. So this is a completely new technology. So what does this mean? This technology means that today it is possible. Today it is possible that we have at about 1,500 TDS, this water, you can have crystal clear water from this device. Now you have deionization. Thank you. You have deionization. This deionization obviously means that you are measuring ionic concentration. This ionic concentration, thank you Vijay, ionic concentration you could measure very effectively, very easily. So this device, which I told you will be there in the field in about 3 months, you can monitor the ionic concentration on your mobile phone, which means that you can track this globally. And that means a very interesting possibility of monitoring health of population. And this is also possible for not only this particular ionic concentrations, fluoride, arsenic, and many others can be done. And today, this industrial unit is ready, and his factory is going to commence production in just about 1 month. And that takes me to another direction. It's just that technologies are required, but it is also important that these technologies are delivered to people. We have natural calamities. Is it possible that during such calamities, arsenic and fluoride containing water, can you filter them in bottles? So we create new bottles, and Ramesh Kumar Soni has produced new kind of water purification devices wherein the water that is transported, many people walk about 15 minutes every day to about 2 hours daily to collect water. During this water transportation with new materials, the contaminated water can be cleaned up, and that is a new product for which we have got a new company, and this company is what is shown here is a multi-barrel containing device wherein ions are doing disinfection as well as cleaning of water. Now, all of this is quite exciting. How about plans for future? Well, it is possible that with new kind of science, it is possible to detect arsenic in water and send it through mobile. And that is there because of new nanomaterials can transfer arsenic 3 to 5 transformation, and in this process, the release of 2 electrons can be effectively taken to electrodes by a process called direct electron transfer. And by this process, we may be in a position to go down to about 2 parts per billion of detection. Today, it is impossible. And we are in that process today. With new materials, I told you about clusters and all that, pH paper-like sensors are possible. And such sensors can really detect a few ions of mercury in just a few seconds. In fact, 80 ions of mercury lead to this, and this science was also done with Professor Vijayan. And a lot of such materials have come. It is not just arsenic or whatever. Many others are possible. What next? What we are looking at is possibility to harvest water. And this harvesting water requires new kind of science to create new materials which are similar to grass. You know, in the morning you have walked and then you will see that dew on this grass. Is it possible to create new materials in the laboratory like grass? And here is that science that is illustrated here, essentially mimicking the science of these namib beetles, which collect water on their wings. Similar science is done, and Dipanjan is doing this. And that science, tomorrow will produce new kinds of purifiers, new kinds of water harvesting devices, and we have floated a new company in this context. Incidentally, an IIT Kanpur student has decided to come to IIT Madras to start a company. So this is also very interesting, that what's the new direction? We are looking at one layer, one atomic layer membranes of this kind, selectively drilling holes in these membranes. This is molybdenum sulfide. When you drill holes selectively, you can create holes in such a way that only molybdenum is there in these holes. And people in this audience have really shown that such membranes, if you create holes by our process, these are atom-specific microscopy, which proves that this is molybdenum, molybdenum, molybdenum. These are actually sulfurs in between. So this is molybdenum-rich surfaces, and with such molybdenum-rich surfaces, you can use white light and produce hydrogen peroxide, and with hydrogen peroxide, you can destroy bacteria in no time. Very interesting new kind of materials, new disinfection is possible. But water is not just this. Water in my laboratory is a material. It's not fluids, sometimes it is solid. So we create solid eyes and look at the science of that. So in the road that is ahead, I can tell you that we can solve all the drinking water problems affordably. We can only solve the problem, but we cannot probably solve the problem in the field, for which something else is required. A better mechanism of monitoring are needed to ensure that nation stays healthy. Affordable and sustainable solutions for water harvesting are needed. We need to create mechanisms for delivery, expanding, of course, the science to clean air, sustainable and healthy water. All that is possible with food. Many things are happening in the laboratory. Global efforts are needed in this context. And it is in this context that we are building an international center for clean water. This effort is happening. What I want to tell you is that every problem is dwarfed in front of this giant water crisis. And India has to take initiative in this area. Right now, there is an Indian a giant mission globally, as well as India is part of this. India is also trying to initiate activities in this direction. This has attracted a lot of attention globally. I've just captured some of that here. And all of these people have been instrumental in building our first company. Anshup, I don't know whether he is here today. Amrita is another BTech student. Both of them are BTechs from IIT Madras. And Shihab is now a faculty member in IIT Tirupati. This boy, Uday Shankar, is a MTech from Madras University. Anil is here, and Kamlesh is here, and this girl is now doing her PhD in Germany. I wouldn't have said anything about this. You know, this kind of science is impossible without a great institution backing. So every time I go elsewhere, I tell my dear director, my dear institution has made it possible. And we live here, of course, coexisting with all of these. And with that, we have built a new department or new laboratory, so to say. And here is a lab. And that lab is fantastic, beautiful. But it has indeed been a very long journey. And I stand here, I was just looking at how did this happen. And this is what it was in 1995. And you know, in this 1995, with this little device, that is an SCM quarter, which is sitting here, I published my first paper. So I have not forgotten those days. Those days were the days wherein you walk around and then grab something, the junk from somewhere. And my lab was built from junk. And today, a lot of students work on different diverse areas. I was obviously not in a position to show you everything that this wonderful set of people do. But we are onto this limitless ladder. And limitless ladder of excellence, limitless ladder of relevance. So hopefully we are in this pastures quadrant. And we hope that we continue to excel in whatever way that we can. And that brings me to this acknowledgement, which I would like you to see. I deliberately did not say acknowledgement to a few people. I came here. It's okay? Is it all right? It's coming? My boy. Give me mic. Sometimes last minute glitches are not going away. So I came here long ago because of P.T. Manoharan. Am I audible? It's okay now? All right? So I deliberately left out a few people. I came here long ago because of P.T. Manoharan. And my teacher, C.N.R. Rao, told me at that point in time, go to IIT Madras, change that place. This is what one day he caught me and told me, while some other job was with me. And I know that Professor Manoharan, characteristic of him, crossed all those hurdles, and finally I was here. And Professor Subramanian, who is here now, Professor Sujit Singh, who is no more with us, Professor T.K.K. Srinivasan, along with a wonderful set of highly committed, stimulating staff. I remember M.S. Moni, our Babu Varghese, Baby, who may be here now, Rama, Devasahayam, and a number of people. That was a fantastic RSIC at that time. It was a time wherein there was P. Vishwanathan, there was M.S. Gopinathan, there was C.N. Pillai, there was C.S. Swami, many, many others. It's a fantastic set of people in chemistry. And I should mention KKB. So with all those people, I could do something. And I felt that I am not in some strange place. Of course, I could do all of these just because Shubha was at home. So she took all the pain on her. Because I was instrumental in keeping her at home, I had to perform at least for 2 people. And I am hopeful that I am somewhat reaching her standards today. My children, of course, brought me joy, not only children at home, children in the lab. Thank you very much. I would be glad in case you have questions or something, it will coming. Yeah. So before I close this, I should say that where there is clean water, there is of course hope, and that hope transcends countries, that transcends religions, that transcends divisions. Thank you very much.